Hi again, everyone. Now we would like to talk about RL transient response. So we would like to talk about this circuit. So we will use the same circuit, except we are going to change the resistors, and we will add two different resistors connected in series, 100 each, and we will connect this inductor in series. Then I will try to see the time constant here by using the oscilloscope. Then I will repeat the same story, but at that time by connecting this guy between this point and this point. So let us see what we are going to do here. This is the circuit. It is similar to what we did. The only difference is instead of using only one resistor, I used one more resistor here. It's connected in series with this. And like what you are seeing, I'm connecting inductor here in series as well to be grounded. This is the inductor and it is grounded. And then this guy is connected to terminal numbers, leg number 6, which is here leg number 6. And then I'm making feedback between 2 and 6. And I'm feeding my input voltage between 3 and 0. So I will feed my input voltage between 3 and 0. I will connect this guy between 3 and 0. But before doing that, I will turn on my power supply. And I will connect this guy between 3 and 0. Then he told me that I would like to measure the output across the inductor. So I will connect this guy in parallel, like what I did here, to see the outputs. I will adjust this guy to a square wave, and I will adjust my amplitude to be peak to peak. This is what he said. And he told me use any frequency, but you should use appropriate frequency. I will start by 50 hertz, like what you are seeing here. This is the waveform that we got. Let me make it a little bit smaller. If I use the channel number 1 to show you the difference, and here I'm moving. This is the waveform that I'm using. This is the waveform that I'm using here. This is the input. This is the input, which is square wave, like what you are seeing. I would like to show it to you. 1 volt per division. So I have 2 volt peak to peak. I don't need this waveform, so I will turn it off. I need right now to see the voltage across the inductor. I started by 50 hertz frequency. I will change the frequency. Let me put like 100 and see what's going to happen, because he asked me to check. I think it is improved. Let me change it to be 500. I don't like that. Let me change it to be 1000. And here I will use auto scale. I think this one is good. We can start using it. So let me make it bigger a little bit like that. So what is needed here? I would like to measure the peak to peak value. I would like to measure the peak to peak value, so I will use cursor. Here I will choose my Y1. I will put it here. I would like to measure this height, which is 1 peak from them. And then I will use Y2, move it here. So I would like to measure the height from here to there, which is approximately something like 1.9 something, which is okay. Then I will try to calculate 63.2% of this height. If you try to calculate it, it will give you delta y, which is equal to 1.219. So I will adjust here this guy to be, instead of reading this value, because I'm going to take 63.2 to find where is the time constant, where is delta x. delta y should be 1.219. So I will move y2 to 1.219. I don't have 19, so I will choose 1.2. That's fine. Then I will move this line and this line. One will be here and the other one will be the intersection at the point, because I would like to see delta x to know the time constant. So this is x1, I moved it over there, and x2, I moved it over there. I am expecting the time constant. Here I found delta x, like what you are seeing, 50 microsecond. If you try to calculate the time constant is equal to L over R, and you know that the value of L is equal to 10 millihenry, and the total R will be equal to 200. So L, 10 millihenry over 200, I think it will be 0.05 millisecond, which is here 50 microseconds. Then he asked me to repeat that story by adding another resistor here. This resistor as if it is connected in parallel with 100, so the time constant will be changing, because the total resistance will be 100 plus 50, which is the equivalent of those two 100. So the new time constant will be 100 based on 150 and 10 millihenry. So L, 10 millihenry over 150, it will be approximately equal to 66.67 microsecond. I would like to prove that. I'll repeat the same story. So what am I going to do? I will connect this resistor, like what he told me, between this pin and this pin. And after that, I will try to adjust this guy, out scale again, and then I will measure this height. So if you try to measure this guy, I will add cursors. So I need y2, y2, this is y2 will be here, and y1, this is y1. So delta y here, delta y, oh, I will change it. I'll put here this guy y2 and this guy y1 to read it positive. This is y1. So delta y, the difference between them. So approximately it is equal to, I can say, like what you are seeing, delta y 918.75 millivolt. So to reach to the time constant value, I will multiply this value by 63.2. If you multiply this value by 63.2, it will give you delta y, which is equal to 0.85. So I need to find delta x corresponds to 0.85. So what I need, I will move this guy down to read here 0.58 or 580. So I will click on cursors again, and then I will move this guy down to read 58 approximately 0. Then I will move x1 over there, and I will move x2. I am expecting the time constant in you, like what I said, 66.6 microfarad. Approximately the scenario here. See delta x? I can make this guy bigger like that, and I can move this guy a little bit here. Yeah, like what you are seeing, 66 microfarad. This is the new time constant based on what? Based on adding this resistor in that way. Like what you are seeing in this circuit, I started without this resistor, then I connected it again to see the change in the time constant. How to calculate the time constant? The time constant is at 63.2 of the value, or the big value. This is what I did here, and the time constant in case of RL is equal to L over R. I'll see you for the last one, which is RLC in few seconds. Bye for now.